So the camera calibration essentially deals with, we want to determine the extrinsic and intrinsic parameters of camera. Okay, so extrinsic parameters are the 3D location orientation of camera when the picture was taken, and intrinsic are related to focal length, the size of the pixels, and so on. So the kind of information about the camera calibration can be very useful for lots of things. So here's one example. Let's say we have a source image and we have a target image, and we want to take this sign and put in this image and move it such that it looks very realistic. So for which you need to know the camera metrics, and you can then see that you can make it a very realistic insertion of this object in this image, as you see here. This is another example. Say this is a source image, there is a person, you want to put that in this here, so it can be like this. Then you can also create a realistic shadow, even though when this picture was taken this person wasn't there. This is in a different image. We can transfer that. And this is another example that we want to put this guy in these images. And this is another nice example. Actually, I'm not able to play video, so I'll get out and play it here. Let's see if it works. So this is from the movie, and what we are trying to insert is this kid here. I think we need to turn off the lights here. Okay. So this is a movie. Do you guys say this movie? What's the movie called? So this guy is artificial. It's a new guy. So we put it so that it looks very realistic. Let's play it again. Okay, so this is on the top of Empire State Building, I think. So this is a real. This was in the movie, but now this kid is artificial, new, from somewhere else, and we are able to insert here nice shadow and all this thing. And the other movie you will see, and then it's playing again. And this one also, this is the same real, but now the guy will appear from somewhere else, and we put in here, and still it looks pretty realistic. So for those kind of things it is useful, and so that's one example. Then we go back, and the other problem related to this is called pose estimation. Now we are given a 3D is this fine, or shall I do the whiteboard like this? This is better, I think. Yeah, so let's say we are given 3D object model, and we have also its projection in an image, and we want to find out the location and orientation of the camera when this picture was taken. It's called pose estimation. Okay, and that is a very old problem, and it has lots of uses. So this is another YouTube video. Let's see if we can play that, which is a nice demo of this kind of thing. So this application in the robots, so there are these objects and we can recognize these objects, there's a cocaine and all this thing, and then we want to find out the right pose of this object, so that then robot can actually go pick it up. So this is recreation of the scene. These are the objects we are interested in, and then ultimately, since we know where exactly this object is located, and then we can take a real robot and it will go and grasp it and pick it up. Okay, so it's all automatic based on the vision and finding the pose, and before that recognizing the objects and so on. So it's going to pick up another thing, the cereal box, I think. So this kind of thing relates to vision and robotics, because the objects are in 3D. I mean, these scenes, the robot operate in 3D world, and the images are 2D. So we need to find out what's the rotation, orientation, and location of a camera when the picture was taken, a location orientation of the object with respect to some word coordinate, so that we can do this mapping, and then we can ask the robot to go pick it up. Okay, so now all this is based on these several transformations, and we have talked about these transformations before, but we will quickly go through them again when we talk about the motion model. Okay, and so the main idea is that we want to relate these different coordinate systems. Suppose there's a word coordinate system, I can know where is the chair with respect to word coordinate system, what is the X and Y and Z, the center of the chair or the table, and then there's a robot where the robot is located, and I can then find out the plane is that what movement robot has to do so that it touches at that center of table, and similarly where is the camera located with respect to word coordinates. When I take a picture, then what pixel this image will appear. So that coordinate system is 2D image plane, these coordinates are 3D, and we have to relate all those to come up with precise model of the camera. So that's what we're going to talk about there. So just simple 3D translation. We already talked about that. If I have x1, y1, z1, then I translate by amount dx, dy, dz, then this will be x2, y2, z2, and I can write down in a matrix form. So it's an identity matrix here, and then these are the translations. So I multiply this with first row, I'm going to get this x2, then second row I'm going to x3, and so on. And these are the homogeneous coordinates, so we'll add 1 to the last element here, and so that we can use this for the perspective transformation and so on as we talk about that. So then the translation matrix is this one. So all these transformations we are going to talk about in matrices, and then there's inverse of a translation, which is simple, that instead of dx, dy, dz, we'll have minus dx, minus dy, minus dz. Okay, and the inverse is that you take a t and t inverse multiply will be identity matrix. So it's a pretty simple thing, and you can verify that. Then you have scaling, which is instead of adding, you will multiply with some constant sx, sy, z. Again, these will be at a diagonal, and all these will be 0 here, and there's no translation. And this is our scaling matrix, and then this will be the inverse scaling, which is 1 upon sx, 1 upon sy, and so on. So then rotation, we already talked about that we can come up with the rotation matrix by looking at this example where we have the rotation of z-axis, and this is the x5 z. Before rotation, it rotates by this angle. Next is x prime, y prime, z prime, and this is the angle theta. So looking at this triangle and this triangle, we have gone through this before. Then you can find out the new coordinate x prime in terms of r, and this is theta, and this original angle is phi, so it will be r cosine of theta plus phi, which will be x coordinate, and similarly y coordinate will be sine of theta plus phi, which is this part here. This is x prime, and you can use the sum of cosine angle and sum of sine angle. You can expand that, and then we know the r of cosine phi is x and r of sine phi is y, so we can simplify that. This become x cosine theta minus y sine theta, and similarly that one. And we can write down this in the matrix form, which is saying that this is the before rotation, this is after rotation around z-axis in the counterclockwise direction. So and we can look at the inverse of this matrix, which is shown here. And so the inverse means that instead of theta we'll have minus theta. Okay, so cos of minus theta is cos of theta, but sine of minus theta is minus sine theta, and so on. So we have these, and then if you take these inverse and the original one, multiply together, you will get identity matrix. So it seems indeed this is inverse of this. Okay, so now interesting thing about the rotation matrix is that to find the inverse you can just find a transpose also. These are the special matrices. So if you take the transpose of this, which means take the column row, make it a column, then this will be exactly the same, as you can verify that. This cos theta sine theta 0 like this, minus sine theta cos theta 0, which is this one, and 0 0 1. So it's a transpose. So either you do replace theta with minus theta, or you do transpose, same thing. And these are called orthonormal matrices. There are certain matrices which have this property, not all of the matrices. And the other property this says that you can take the two rows or two columns of these matrices, find the dot product, then it will become 0. So suppose this one cos theta sin theta minus sin theta cos theta will cancel each other 0. But if you take the row and find dot product of itself, so it will become cos square theta plus sin square theta, which is 1. So if you take the row which itself will be 1, if you take the row and another row, it will be 0. So that's the orthonormal matrices. And you can do the same thing for the columns. It's true also. And we are going to use this property in later when we talk about calibration. Okay. So we also talk about Euler angles. These are the rotation around arbitrary axis. We can break this into 3 rotations: rotation around x, y, and z, and then we can linearize it. This is non-linear. Each term is non-linear because it's sine, cosine, and so on. It reduces to this, and that's the approximation of the rotation matrix. And we have also talked about the perspective transformation. So this previous transformation was from between the 3D coordinates. Now we are talking the transformation between the word to the image. So we have the x, y, z here. We take a picture, looks like that. This is the pinhole. This is just a one hole where the ray of light is going through. It's a simple camera model, and hole is basically a lens, and the distance from the image plane to the lens is f, which is the focal length. Distance from the lens to the object is z, which is kind of depth. So this is y in the word coordinate, and this is y in the image coordinates. So when you take a picture, the picture is upside down. So that's what it will look like that. And that's what actually when picture is formed in your eyes is upside down. You have a way to invert it. So now we have these 2 triangles. So we can look at these equivalent triangles. This is this side upon this side. Then we have this side upon this side. They are equivalent. So therefore y can be given by this. Similarly, you can come up with x. So which means x and y are modulated or modified depending on how far they are, and that's the fact in perspective transformation. So now if the origin is at the image plane, here the origin was here at the lens. Now if the origin is image plane, then you can do the same thing, but just these things will change. So here we will have minus y here, and this is y, that's fine, this is f. But now this distance is the, from here to here is z minus f, because from here to here is z, but then we have to subtract f from here. So therefore, because the origin we have shifted to the image plane, so that's what we will get. And so y is given by this and x is given by that. Depending on where the origin is, these equations change a little bit. So now it'll be interesting to come up with the metrics for perspective transformations. Like we have matrix for translation, for rotation, scaling. Now we want to do also perspective transformation, and that was the reason that we introduced homogeneous coordinates. So we want to come up with some elements here so that we take the word point, maps to the image points, okay? And that will be the homogeneous coordinates, the word coordinates. So as we talked about, the homogeneous coordinates you can get from the Cartesian coordinate, which is x, y, z, just adding the fourth element k, multiplying each of those elements with k. So instead of 3D vector, now you get 4D vector. And then you can go back from the homogeneous to the Cartesian, just take the fourth element, divide by each of these, and you'll get like that, okay? So if you do that, then the perspective transformation or projection will have this matrix, which has the focal length. As you saw, that the perspective transformation equation has a focal length there, and this is what we get, and you can verify that. So if this is our matrix, perspective matrix, then we take the word point, x, y, z, convert it into homogeneous coordinates like this, and we get the homogeneous coordinates in the image plane, and which is shown here. Then we can multiply this with the first row, we'll get kx here, second row we'll get ky, kz, and this last one we will get the 0, 0 and minus kz upon f plus k or minus k. So minus kz upon f plus k, which I've written other way, k minus kz upon f. So this is perspective matrix. I want to find the image coordinates in a homogeneous system, which is this one, and this is what I get. Now this is a 4-dimensional vector. I need to convert to 2-dimension because image coordinates are only 2, x and y. So what I will do, I'll take the fourth one, divide by the first one, that's x coordinate, take this fourth one, divide to the second one will be y coordinates. Okay, so let's do that. So if I do that, kx divided by this, which is here, so then I can take the f on this on the numerator, and then this k will cancel because k is common in those, so it becomes f minus z and fx. Similarly for y, f minus fy upon f minus z, and these were the exact equations we did before when the origin was at the image plane as compared to the lens. So which means that these are exactly same equation as we derive here, just to make sure, same equations, and we are now able to express these in terms of metrics. And perspective transformation matrix is this, which is very simple. Just have one unknown, which is the f for the pinhole camera, minus 1 upon f, which is the focal length. Okay, so that's very nice. So now let's look at,
How do we get the k? Does it matter?
K is any constant, anything. Just you can define anything. Okay, so so let's look at a simple camera model that we will use these transformations to, make it realistic. So let's say camera is the origin of the word coordinate. So maybe word coordinate is here somewhere. And then we translate the camera by some amount, say G. It's a 3D translation. So suppose we take it and put it here. And then we rotate around Z-axis, some rotation to get the scene. And then let's say we rotate again on X-axis, you can do that. And you have to know which direction you are rotating, clockwise, counterclockwise. As you know that if it's clockwise, then it is inverse of counterclockwise, so you need to make sure. And then you translate again maybe somewhere. And so for everything when you do, you have a matrix. You have to keep an account of that. So we started with some point. We are looking at the word points, maybe some chair there, for which we have a word homogeneous coordinate. This is the first translation, which is here, translation. This is the rotation on Z-axis, which is this one. There is rotation on X-axis, which is this one. Then another translation. Then we take a picture, which is the perspective transformation, the P. And these will be the image coordinates in a homogeneous system. Okay? So all these things we have to keep in account to relate the pixel coordinates with the actual word coordinates in 3D. Yeah. Yeah, the order is important because they're not commutative. So this is just one example. We just did that. But you could do another order. You can do more rotation, more translation. Whatever you do, you put those matrices. Then it will work. Yeah.
So why did we do another translation?
I just like it. Just added it.
Okay.
You can just get rid of it. Okay. So then we'll get rid of that matrix. That's it. This is just example. Okay. So now one thing is that the in this thing what we are doing, we are translating, rotating the camera, and then we are taking the picture of the scene. So all this is relative. Either camera is fixed and the object rotating and translating and so on, or the camera is rotating, object is fixed and so on. So we just have to make sure that what we are doing now, when we consider, since we are taking a picture of the scene, say there's object there, then for these transformations, and the camera is rotating, so we have to use the inverse transformation. If the object was rotating, then we will do the forward transformation because it's relative. So the same, we want to make sure like that. So keeping that in mind, then we have these transformations, and we have these matrices. We already talked about. So we have first one is our G matrix, which is the translation in x0, y0, z0, and we have put the inverse here because we are translating the camera, not the object. And then we have the rotation around, the z-axis, which is this one, and this is again the inverse by angle theta, which is this one. Then rotation on x-axis, which is this one, and this is the last translation, and this is our camera model, the perspective transformation. So you'll get these matrices multiplied together. You will get the homogeneous coordinates on the left side, and then you can find out the image coordinates, which are the x. Take the fourth component, divide the first one, divide by that, take the second one, divide by fourth, and this is the expression you will get, the image coordinate of a point in 3D with all these transformations. And that is a very simple example of a camera model, which has the rotation, translation, and perspective transformation. Yeah.
When would we use this model versus the model where we rotate, like where we use the object that we're moving? Is it maybe, for example, when we're having a robot and we say we want to know how far he has moved.
That's right. Exactly, yeah. Yeah. But these are exactly same concepts, just have relative, That's right. So so that's it, So now the question is that if you knew all that, if you actually had taken a camera, you know exactly how much you translated, how much you rotated, and what you did, you can plug in those numbers. Then you know any point in 3D, you can find this image coordinates according to this model. But now, how about you don't know? So we want to talk about how can we determine the camera matrix. And if you take all these matrices, there are lots of matrices, multiply them together, again you get one matrix, right? Which we'll call A matrix. And so what we want to talk about, that can we find out this A matrix by knowing some 3D points and corresponding 2D points, can we find out this matrix, and that's essentially called camera calibration. Okay? So now as you see that in this 4x4 matrix, there are 16 unknowns, okay? Which are the A's. And we know that the homogeneous coordinate, first one, the x1 is given by this, multiply this with first row, and CH2 and so on, and CH4. We are not going to use CH3 because the image doesn't have third coordinate. So now, so actually we have then 12 unknowns, 16 unknowns. And once we know these homogeneous coordinates of the image, then we can find out the Cartesian coordinate by dividing by CH4 in both cases. So therefore, we want to talk about how, Channel 1 what? CH1 divided by CH4. So this is so as we talked about, when we multiply, this is the homogeneous coordinates, you multiply this, you get image homogeneous coordinates. Now from homogeneous coordinate to go to the Cartesian coordinate, we will divide by the fourth component. And if you take the Cartesian coordinate to go to homogeneous, we will multiply by that and add that fourth component. So that's what we are doing. So so how we determine the camera matrix, as told you that what we are going to do, we'll select some known 3D points, x, y, z, and their corresponding points in the image, which will be small x, small y, and we will solve for camera matrix element using least square fit. Okay, and let's say you will take this kind of checkerboard pattern, you will define some coordinate system, maybe here's a 0, 0 origin, and you measure these, what are their x, y, z coordinates, and so plane, so the z will be, if it is just a straight, z will be the same, but still a little different. And then you'll take a picture of that, which is this one, and then you can determine the image coordinates in terms of pixels. So using these two, we will find out those 12 unknowns. So these are the x, y, z, these are small x, small y. These are the word coordinates, these are the image coordinates. So that's what we have here. And this we already talked about. That CH1 is given by this, CH2 is given by this, and CH4 is given by this, and this is x, this is y. And we don't have to worry about CH3. So now we can simplify these further, and we essentially have to have just two equations because they're x coordinate and y coordinate. So we are going to plug in this value here and plug in this value here, and so this will become a1x plus a12 all this minus plus a14. Then we bring in this side here, ch4 minus ch4x. Okay, so this is ch4, so it'll become minus a41 uppercase x and small x, minus a42 uppercase y and small x, minus a43 z and x, and minus a44 and x. So this we'll get from first equation. Similarly, this we'll get from second equation. So we'll get these two equations for each correspondence. So 3D points corresponding to 2D points. 3D point xyz, uppercase xyz. This image point is small x, small y. And what we are going to do, we'll get many points. Okay. So n points will give us 2n equations, and we look like that. The first set of equations are the where we get from the x1, second set of equations are from the y1, and in this we have 12 unknowns. Okay. So other thing we have here, that the right side of all these equations 0, which is which is shown here. We can put in matrix form here. So we multiply this one, get first one, second one, and so on. So we have n from the x and n from the y. So this is called a homogeneous system because the right side is 0. So this is infinite number of solutions. There's no unique solution because on the other side is 0. So therefore what we are going to do, that we will pick one of the element f or 4 as 1 and try to find a solution. So so that if you do that, then this system, as you see here, as I showed you before, will become like this. So we have like this is the same thing here up to a44, but now we are going to make this 1, and then it will disappear here, and we will have the less unknowns, 11 unknowns, and we will have these equations here. Okay, so and what we are going to do, that since a4 in this one is now known, which is 1, so we can take this column and move it on right side because these x's and y's are known, so which are image coordinates. So therefore this will become like that. So now we have this matrix which is known, this is known, and this is unknown. So this is the linear system. Okay, and again, this is not a square matrix. It's we need to find the pseudo inverse. So always we do multiply by the transpose on both sides. Say D transpose, we'll call this as a D matrix, and then we will take this here because now it becomes square, because this was here 2n by 11, and now it will become 11 by 11 because of the transpose multiplied by D. So then we can find out a Q, which is these unknowns, and this is the same thing as we've been doing again and again, least square fit. Okay, so now once we know that, once we know the camera model, this matrix, then I think we can do interesting things, that from the camera matrix we can find out where is the camera when particular picture was taken, where was the location of a camera. Okay, so the idea is that so if you take 3D point, say let's say this is 3D point and image is formed here, and because this ray will come and hit through the lens, and for that 3D points, let's say we look at homogeneous coordinate. Now in homogeneous coordinates, if we make the third component 0, then you get another 3D point which let's call x11, and this is a 3D point, but this lies on the line which connects this x1 with the lens. Now image of this point will also be exactly same, because all the points lying in the line will have one image. Okay, so that's one thing. So which means we can find out a line in 3D knowing the one 3D point and corresponding point of the image. Let's look at another 3D point, which is x2, and we can do the same thing. This image is formed here, and then we find another 3D point on the same line by replacing the third coordinate there, 0. Now we have two 3D lines. They will intersect, and that will be the location of the lens of the camera. So we can find out location of camera by using that one, so which is very interesting. So second thing is that we can also find out the camera orientation, that what was the orientation of camera when the picture was taken. And that's also a very interesting way to do that. It's very simple. So let's say, we have object here, we take a picture, and this picture looks like that. Now let's say we move the object a little closer, and picture is moved like that. We move it further, pictures move like that. Now what's going to happen when the object is at the center? Where will be the picture? It will be, see, it's, as you see, it's becoming bigger and bigger. Now when it's exactly that, then where will that be? It will be at the infinity. Okay? Be, So, because these are basically parallel lines, like infinity when the object is at the lens. Okay, so now when will the image coordinate become infinity in the Cartesian according to bottom infinity? What's the condition? CH4 is 0. Okay, so which means that the CH4 is 0 is the condition, and this is the equation of a plane. And from here you can find out the orientation of plane. That's the orientation of your camera. So which is very nice. And you have these are your camera metrics. Okay, so again let me explain. So we want to find out the orientation of a camera. Okay, and what we are doing, that we are looking at how the image is formed. We have object in the first row, the left side we have object there, and then object is formed, image is formed on the left side. Then we move object closer, and image is bigger. Then we move even bigger, closer, then it's bigger. So we keep moving, and at some time we actually put the object right at the lens, which is hypothetical. We put it. So which means in that case the image will form at infinity because it's a very large. And when at infinity, then we look at this equation. It'll be only at infinity the CH4 is 0 because you are dividing by 0. Then when you use that, and that becomes the equation of a plane. And then once you have equation of a plane, then you can find the orientation of plane, and that orientation of plane is the orientation of camera. So that's the reasoning behind that. Okay, so let's look at some examples. So here is the camera matrix. This was in San Francisco, and this is a map of San Francisco. How many people have been to San Francisco? Very few, yes, and amazing. San Francisco is the most popular city, people visit. Anyway, so this is the big milestone. San Francisco is this pyramid and all these kind of these streets. So given that camera matrix, then they found out that this particular picture was taken at intersection of California and Mason Street at the elevation of 435 feet above sea levels, and this was the angle at, oriented angle 8 degrees above the horizon, and these are the focal lengths and so on. So you can, this is a picture for taking long time ago from the book, so you can find out that where this picture was taken, which is pretty interesting. Another example here, this is camera matrix, and this is another picture, and they found out that this was taken at this elevation, and the camera was oriented that, and this is the location of where the picture was taken. Okay, so there is a nice little paper which described that, and actually I got an email after one student from Cuba, he listened to my lecture, and he sent me email that he doesn't have access to this paper, so we scanned the paper and emailed to him. So it's a good service, because Cuba is very hard, I think, to do the photocopy or something. Okay, so camera parameters. So what we are saying, that one way to do camera calibration, camera model, is that you know precisely what are these angles, rotations, and translation, so on. Another way to do is the 3D points, the corresponding 2D points, you find this A matrix, the A's, as we talk about using least square fit. Now that does not actually tell you precisely what are the extensive parameters, rotation, translation, so on, and this was one example that I showed you can be done. So in general, we want to be able to estimate those extrinsic and intrinsic parameters. So we look at this a little bit more in detail. And so again, extrinsic parameters are the external parameters which define the location and the orientation of a camera. And then these are 3D translation and 3D rotation. And intrinsic parameters are the internal parameters of the camera, which are the focal length and all other things. Okay, so we are going to talk more about that. So now we are going to look at this camera model, very similar to what we talked about before. So we have x, y, z, and that's a word coordinate. We have a rotation matrix and we have a translation matrix, and we will use these notation. These are the word coordinates here in the homogeneous. So we can multiply these two matrices, we get this one. This contains the rotation and translation. And then that's one thing. And then we will call this matrix is mx, because extrinsic, capturing the extrinsic parameters. So then we also have to put in these perspective projection, and this is your object, and this is the lens, it's here. And now what you're going to do, just to be consistent, we're going to move the image plane in front of the lens, just to, so that we don't use the minus sign. So now image plane is here, so the lens is here. It's just reverse that. So these images are not upside down now; they are actually same. So origin of the lens, image planes in front of the lens. So therefore now we don't have a minus sign. So y is fy upon z, x is equal to x upon z. Okay. So then the perspective matrix we can represent like that, which is simpler now. That we have x, y, z, we multiply with this, and this will become fx, this will become fy, and then this will become z, and we can convert into the Cartesian coordinates. We divide by the third element, fx upon z and fy upon z. Okay, so that is one thing. So now we are going to look at all these things in terms of the image coordinates and camera coordinates. So we have these notations here. So these are the camera coordinates. Then we relate this to image coordinates, which are this one, and this is the center of the image in terms of pixels, and these are the scaling things which will give you effective size of pixels. Because see, you have pixels and you have these millimeters, you want to relate these, so you have this scaling thing in horizontal vertical direction. So essentially what we have, we take the image coordinates, it has to be with respect to these image centers, so we subtract the centers and then we multiply by scaling factors in vertical and horizontal. So this is relating the image with the camera coordinates. Okay, so this then can be rewritten that if we know the camera coordinates, then we can find out the image coordinates by using the center of the image and all these things, so which is simple. So then this can also be written in a matrix form. So we have 1 upon Sx, 1 upon Sy. These are the translations from the center, like that. So what that means now, we can put again these matrices like that, and this. So first thing here is we are looking at the rotation, any rotation. So the first example I gave you a long time ago, which was particular rotation on z-axis, y-axis. Now you have rotation matrix, which capture any rotation, 3 by 3 matrix. And then we have perspective transformation, which is F. And then we have these from camera to image, we have that matrix. So this is kind of complete camera model, will capture anything. And that's more general. And again, we have the homogeneous word coordinates and we have the camera coordinates in the, image coordinates in the homogeneous system. So we can take these matrices, multiply together, and first simple thing is that we can multiply the these two matrices, which is very easy, which you will get like this, and then you have this, and then now this is the extrinsic matrix, which is capturing the location orientation. This is the intrinsic, which is capturing focal length and all other things related to that with the camera, and that's what we have here. So we multiply these two, we become one matrix, which is called M matrix, and it's a camera matrix which capture everything, and which was A matrix in our case before. Okay, so that's that, and we can again multiply these two matrices and we come up with like that, the monster matrix, all these terms there, and becomes like that. Okay, so and we can simplify this with that scaling, because the focal length, then there's a scaling, different scale in x direction, horizontal direction, and different scale in y direction. So we'll just call that fx and fy. So we can get rid of this denominator here, so it'll become fxr11, all this become fx and all this thing. So this is all the camera matrix. As you see, this says everything, the rotation, R11, R12, all rotation thing. There's a translation, x, y, z, tx, dy, z. It has those focal lengths in x and y. It has these image, center, ox, oy, and all kinds of things. So our aim is to find this camera matrix, and we can do the same thing, that we will have 3D points, known 3D points, and known 2D points. We already know how we can estimate the camera matrix. We already talked about using least square fit. So once we have that matrix, the A matrix, then we are going to talk about from there how we can estimate the rotation, the translation, the focal length, and all those things. That's what we're going to do. Okay, so let's talk about that. So this is the we'll call M matrix. And as we talk about, we don't have to worry about the fourth row. So this is M matrix, and this is what we call, we used to call A matrix, but let's call M matrix to be consistent with the notations. Yeah.
Just have a conceptual question. So
yeah.
Once I have, so the idea is that I'm moving my camera around, and then I try to get that M matrix, and at that point, nothing will change with my camera, so that every picture that I take after that, I can derive.
Yeah. But as soon as you change the camera, you'll have different camera metrics.
That's what I was thinking.
So now in that one, the intrinsic parameters may not change if you're not going to change the focal length, everything, but extensive will change. The orientation, location will change. Then you'll have different camera metrics. So that's the problem. That's a hard problem. So the method, which is called a structure from motion, that will take a sequence of images taken by a moving camera. It will actually estimate the motion, location, and the rotation in every frame. So it's actually doing that camera calibration in every frame. So that's we're going to talk about that. But right now we are talking just single image, and we want to compute these extensive parameters for that. As I showed you San Francisco image, those were the extensive, where the camera was located, when the picture was taken, how it was oriented, and so on.
So
yeah.
You showed that one picture that was just the checkerboard. So would we use an image like that first to get the M matrix, and then we would, not moving the camera, not changing anything, then we would take the actual image?
Yeah, that's right. And then see then if the camera is moving, then you have to put the checkerboard again and again, right? So then the answer to that is what a structure from motion does, that you don't have to have a checkerboard. You can have any interest points, and if you can say these interest points in this image are the same these interest point in this image, like shift and matching, then you can do essentially the same thing as you are doing each individual images. Okay, so we're going to talk about that. Okay, so we have now somehow using the 3D known points and their corresponding 2D points as we did before. We got a matrix. We are going to call that M matrix just to be consistent with notation of the rest of the community. And that's his M matrix here. It's an M hat. Okay, so estimate M. And this is our real camera matrix, which is in terms of these parameters which we want to compute. So we want to compare these two matrices, and these will be the numbers as we show 1.3, 2.9 or something. Now each of this element is related to this, which has a meaning. That is a focal length, there is rotation, element, and translation, and so on. That's what we want to find out. Okay, so we are going to estimate. We have estimated matrix M, camera matrix. Now one thing, do you remember that we got the system was homogeneous, so the solution was not unique. We arbitrarily selected one of the element as 1. So therefore, these solutions are up to scale factor. If the solution is, say, A and Q, then 2Q is also a solution. 3Q is also a solution. So therefore, M hat is same as gamma M. It is a constant being multiplied. So that's one thing we want to keep in mind. Okay, so so now we are going to relate this M matrix with that camera matrix with that gamma, which is a constant. And so what we are going to do, the first thing is we are going to, and in doing so, we are going to use the properties of the rotation matrix we have learned, which are very important here. So what we are going to do, that if you look at this is a row from a rotation matrix, is that right? It's a third row of rotation matrix. Rotation matrix is 3 by 3. R11 to R13, R21 to R23, R31 to R33. So what did you learn from rotation matrix? That if I take a row, multiply with itself, then it should be 1. If I take a row and multiply with another row, it should be good. So therefore, we are going to take this row and multiply with itself. So that's the dot product of this. So it will become R31 square plus R32 square plus R33 square, that one. And then we are going to corresponding elements M31 square, M32 square, M32 square. And we'll take under root of that. And so this one is what? This is 1, yes? So therefore this will be gamma. And which means we can determine the magnitude of a gamma, the scale factor, by finding this. That's the first thing we're going to do. Because we have this matrix, we have those m's, we just find the magnitude of that and square, and that gives us a gamma, but it's only magnitude. We don't know the sign. Okay? So that's first thing. So then what we are going to do, that we want to get, in order to get rid of a scale, we are going to divide each element in this matrix m by that thing, so that we can get rid of a scale, but only a sign will be a problem. Okay, but we'll have the same thing again here. So now the way we are going to do is, since we have used R31, R32, R33, so we are going to do this in a sequence. So we're going to compute TZ, and we are going to compute the third row of rotation matrix. Once we know that in this one, then we are going to compute in this term, this row. If we know R31, then we'll show we can compute OX, and similarly OX, and then we will talk about that we can compute OY also. After that, when we know OX, OY, then we can compute FX and FY. After that, then we'll compute the second row of the rotation matrix, and then at the end we'll compute the TX and TY, which are shown here. So that's the way we're going to do. So let's start doing that. So this is the same thing as you have been seeing. So now let's talk about TZ. So TZ, this is equal to M33, which is, we can compare this component with this component. And M34, M34, which is a fourth component here. Now, only thing is that, we are already taken care of the magnitude, but the sign. So this, we don't know the sign. It can be positive or negative. So TZ is equal to sigma M34. So sigma can be +1 or -1. But we can determine this easily, that this is a TZ is a translation depth. Now, if the origin of the word is in the front, then TZ is positive. If the origin of word is in the back, then it's a negative. So we can determine sign very easily what TZ. Okay, so that's easy now. So now we can, since we know TZ, we know sigma, then we can compare from R31 and M31. We can find R31. From here, comparing this with that, we can find R32, and we can find out R33 comparing this with that. So now we know this one, we know this one, we know this one, just comparing these two matrices. And we have done it. The first thing, we used the fact that this is the orthogonal matrix. Take a row, find a dot product with itself. It's 1. We find the sigma, and then we have these isolated terms. We found a sign using the translation and Z, and once we know that, then we can find out, because this matrix is equal to this matrix, which means component wise we can compare. This will be equal to this with the sign, and sign we determine from TZ. Okay, so that's, so far that's what we have, which means these red boxes are computed already. So now since we computed R31, so we're going to try to compute OX. So what we are going to do is we are going to look at these. The first row, 3 terms we'll call Q1, second row we'll call Q2, third row we'll call Q3. Now what we are going to do is finding the dot product of Q1 with Q3, like this one. Dot product of this with that, which is given here. Now this has to be equal dot product of this with that. Okay, so let's see what that will be. So this is the first row, the 3 terms which are shown here, and Q3 is here, R31, R32, R33, which is this one. So you want to find dot product of 2 vectors, and so which means this multiplied by this multiplied by this, and this multiplied by this, and this has 2 terms, so we'll have 2 terms like that. So first will be fx r11 and minus fx r12 minus fx r13, dot product of that with this, and second is take R31 OX, R32 OX, and this one, then dot product against by this. So we have now 2 terms. Now tell me that which should disappear. The first one or second one? Second one should disappear. First one should disappear. Let's take a vote. First one should disappear because the third row and the first row of rotation matrix are find dot product be 0. Yes? Because the R11, R12, R13, you can take fx common. So it's just, that is the first row of rotation matrix. This one is third row of rotation matrix, R31, so when you multiply and you find dot product, it will be 0. So then the first term will disappear. Second term will give you what? 1 and then OX. Okay? So that's what you have. Great. So we can find OX. Finding the dot product of Q1, which is the first row, the 3 elements, third row, 3 elements, we can OX. So it's very nice. And if you can do OX, then you can do OY also. And what are you going to do with OY? To do OY, what are you going to do? Which row you are going to use? Second and third. No, because in this one you use first and second, you use second and third, which is shown here. Okay? So far we have like this. So it's time is up, so let's end it here. It's a lot of fun. So with that, now we have determined these elements, and we already know R31, R32 and so on. So then we can try to find the other elements in these. And the next thing we are going to do is we will do the dot product of Q1 with Q1. So these 3 elements with these 3 elements, which is in here, and corresponding 3 elements from here with itself. So these are the 3 elements here, minus fx r11 plus r31 OX, and this one, and just repeat that. So then again we have this kind of summation thing here, so we'll separate these out. We will take this thing and this multiply with this square, this multiply with this square, and so on, and which is easy because it's the same thing. And then we can further simplify this. Now what's going to happen, this is like a plus b whole square, so it'll be a square plus b square minus 2ab, and similarly we'll have these terms. Okay, so what that will give you is the terms which will multiply r11 with r31 and so on. So those are third row with first row, they will cancel. So this you can simplify. At the end you will get fx square, and then you will get ox square. And since we already know ox square from the previous one, that's what we did here, then we can find out the fx square, which will become this minus ox square under root, so it's fx. Now same thing we can do finding the oy, which is the second row, and that will become symmetrically like this one, q2 with itself minus oy square. So which is good. So which means we have these elements here. Still there are some of the elements are missing, especially tz and ty. I mean tx and ty, and also the rotation. So what we will do is now compare. We will look at this element, and this element should be equal to this with the sign, which is sigma. And in this one we already know ox. Okay, we already know r31, we know fx, and we know r31 ox. We don't know only r11, so we can find out r11 by dividing fx each other element, and then moving this m31 ox m31 minus m11 divided by fx, and that will give you the r11, and then we can find out the r12, r13, and so on. In the same way we can find out the second row of the rotation matrix, which is here, and exactly same. Now here we are going to look at the m31 minus m21. We are going to subtract the these two or these two, and that will give you the r11, r12, 3, r21, r12, and r23. And then once we have that, then we only have to determine the tx. Okay, so tx will be from here, and ty will be from here. Again we look at the corresponding elements, so m34 subtract from m14 and this is multiplied by fx, we divide by that and simplify, we get tx and ty. So that is the way we go through systematically compute this. Yeah.
I just want to make sure those ox's here in the lower part and oys are the same as the lowercase o sub x.
Yeah, they are the same thing. Yeah. So this ox to oy, these are the image centers, and these are they different font or something?
No, it's actually 0 sub x.
Oh, okay, yeah. So we should change that, you know. So let's try if we can do that right now. This one?
They're all the 0 sub, it's all 0 sub x and 0 sub y, all of them.
Oh, okay, good. So we can change this thing. 0 and O looks the same, similar. So
There's one more.
one more. Okay, good. That's it.
Yeah, and this one.
Okay, very good. So how about these is okay?
There's 2.
All of them should be.
Yeah, all of them.
Wow. So it seems you guys are attentive, huh? Nobody else found out this thing.
I like the 0, it make it very easy.
Oh, I see.
Oh, it made the calculation easy.
But then the whole thing will become 0. How about this one?
No, they're all fine.
That's fine,
That's
okay.
why I got confused because you used
Yeah.
different.
Okay, great. So that's it. So I think that what this is saying, that all these things you can do if you go through systematically, if you know what's the rotation, what's the translation, how the perspective transformation work, you take all these things, multiply these matrices and so on, then you compare, and you can go. Each step is pretty simple, but you just have to keep doing that and do it logically. So there is, I covered this in detail in the chapter 1, and also there is this reference you can look at, and that paper I mentioned to you, the pictures when they took from San Francisco, they have details about that. Okay, so that finishes the